All right, so I forgot to mention last time, but I posted an announcement about this for anybody who missed it. And maybe I'll just share a screen here. I think this is one. All right, so what I've got here up on the screen is the Canvas website. And so I know that some people are going to have a cramped final schedule. As you might know, that they do not allow us to do anything during the normal finals week this semester, primarily because they are taking the original finals week to be the beginning of what they're calling innovation quarter, which is a totally optional but a set of curriculum that students will have access to and be totally free. And the first week of that is Innovation Week, which takes place at the original finals week. And they wanted to make sure that no content from this semester bled in the Innovation Week so that students would sort of be free and available to participate in Innovation Week. And so because of that, that's the reason why the last week of the semester, you've now got everything to do during the last week of the semester as usual, plus all of your finals to deal with. And so we are not allowed to offer finals during the actual finals week, or we're not technically allowed to offer anything during that finals week, even make extensions and things like that. And so it puts everything quite a cramp. Now, I know that some of you are going to say, well, we've got this two-stage exam in 325. Our 80% individual exam is going to be on Thursday, and our 20% group exam is going to be on Friday. But I already have 3 other exams on Thursday and 2 other exams on Friday. So what do I do? And I appreciate that. And so what I've done, and although I don't know if I'm technically allowed to do this, and so if you like this option, it might be easiest to keep it between us, because if anyone above me finds out that I do this, and I might be told that I'm not technically allowed to do this. But so the options, in Canvas, if you go into the people area inside Canvas, then you should notice that up in people, there's a groups. And if you go into groups, then there you should see a couple of final exam groups. It's a final exam groups here. And everyone by default is in this early exam group. So this is the Thursday, Friday setup on December 3rd and 4th that I was just talking about. Now, what I am doing is I am allowing you, so because I'm a test user, both of these are locked for me. I'm not a real student, but for you, you should see an option here to join this later exam group if you like. And it will move you from the early exam group to the later exam group. Now, what happens when that happens? So you need to do this before December 1st. So December 1st is the deadline to do this election, this kind of self-enrollment. But then on December 1st, I'm going to turn these groups into sections where I can assign a different due date or a different sort of accessibility window or assignment window for those 2 different exams. And so for those of you who elect to move yourself into the later exam group, then your individual based exam will be the Monday, December 7th of the original finals week. And your group exam will be the Tuesday of the original finals week. And so the loophole that I'm trying to work through here is that you have to have the option to be able to complete all work for the class before finals week. And so you do have that option. But if you would like, I'm providing you the option where you can instead do the Monday and Tuesday of the original finals week. Now, if you elect to do this, you will not have access to the final exam on the Thursday, Friday. Likewise, if you elect to do Thursday, Friday, you will not get a second shot at it. You only get 1 shot at the final exam, but it's a 2-stage exam, so it's got this 2-day thing. So you get to choose whether you want to do that in the early case or the later case. On top of that, if you click the little arrow next to it, you can see whoever else has elected for the later option. Why is that useful? Because on your Tuesday here, then that's the group one. And so these are the other people who will also be taking the exam then, and you can feel free to collaborate with them. And so this makes it easy to find people who are taking that group exam together. Likewise, if you're interested to see who's taking it early, then it shows everybody. Currently, everybody but 1 person right now is automatically enrolled in the early exam group. So I explained this setup in one of the course announcements. So if you go to announcements, you can find instructions for that. I also have a post under this exam flexibility announcement down here. If you go to the Slack page, there's also a post about that that gives instructions for it. But just to see it again, you click on the people group, then you click on the groups tab. You should find these groups here. And for you, you should have the ability to join the later exam group if you wish. You don't have to. But if you do, you will not get access to the exam on the Thursday, Friday, but you will get access to it on the Monday, Tuesday. Do this before December 1st. And so I could write that here. So before December 1st, maybe I'll make that a little bit more permanent here, just so it's burned into the video. December 1st deadline. This is supposed to be deadline, but this is my mouse writing. I hope my stylus writing is a little bit better than this. And that is the people group, or the people tab, and then groups on Canvas. And then you can then choose here. You'll have that option to make your choices there. All right, are there any questions about that? Provide you a little extra flexibility. Okay, great. So I will now get back to the original content. All right, there we are. Okay, so we are now finishing with timber management today, and then we'll start talking about fisheries management, and then that should hopefully wrap up all of our renewable resource content. Oh, I missed the chat things here. Okay, looks like great. I'm glad that you appreciate those options, and hopefully that'll provide you the flexibility you need. I just want to make a couple of kind of big picture comments about, let's make this a little bit. All right, so the kind of big picture comments about the forestry economics, or about forest economics. And I am going to sort of tie this back to our discussion of economic rent in the non-renewables. And hopefully this will help answer some of the questions that came out of the muddiest points, for example. So we started out with the biological rotation. And so you can think of that as a kind of myopic case. So the myopic case is, how do I maximize revenue at a particular price? And the way you do that is by maximizing volume. So you maximize quantity or volume. And so as a supplier, I want to push out the highest amount of wood that I can for any unit time. And so the biological rotation is what does that. And so the biological rotation is, in a sense, the most efficient way to produce timber in any unit of time. And so in the biological rotation, the idea is that we've got our volume characteristics here. So we've got, for any time, and that's time, you can think of this as rotation duration. And we've got volume on this axis, and the idea being that this is the volume of timber that we'll say produced. And so what we notice here is that there is, if we look at the slope along this curve, so each one of these are little delta V's. Then what we see here is that the year to year change rises initially, then reaches max, then falls. So in other words, initially you get slow growth, and then it gets faster growth, and then you have the fastest growth, and then you get slow growth again. And so what we need to figure out here is as things slow down, what is the minimal amount of growth from year to year to year that we tolerate in order to maximize our revenue. And so actually the way, and this is what I've done here in the notes, is if I want to turn this into revenue, then let me just, instead of plotting volume, let me view this as actual revenue. And in which case, this curve is not, you don't view it as V of t, you can view it as P minus C times V of t. So if I decide to cut at any particular time and then sell that wood, then this is going to be the revenue I get per rotation. And what we're seeing is that the revenue, as the rotation length grows, the growth in the revenue is increasing until I get a maximum growth in revenue, and then I get to fall off in my revenue for longer rotation times. And so I need to figure out at what point does my my delta V get small enough that I cut and then restart so that I get growing growth in my revenue again. And so what we found is that if you draw a, oh, my screen broadcasting just stopped on me for some reason. So give me a second to rebroadcast. Okay, and I don't think I'm broadcasting yet. So let me reshare. All right, I think, am I back? Let's see. If I draw a little circle, good, I'm back, all right. It's been a day of technical challenges for me, so for some reason, I apologize. If I want to figure out when do I cut, then what I look at is my long-term growth over the rotation. So what is my average growth? And I want to make sure that my instantaneous growth is always above my average growth. At the instant where they meet, that's when I stop cutting, and that's how I maximize my revenue. So this is the kind of myopic perspective. And so if I draw this line that's tangent with this curve here, so it's tangent right about there. So this is my point of tangency. The slope of this line is is going to be V over T divided by T. And this is known as the mean annual increment. And then if I just multiply that by P minus C to convert it into revenue. And so this is my, my revenue growth. So the average revenue I get divided by the length of the rotation. And what this point here, this is when the instantaneous change in revenue falls to the long-term average. And so at that point, my delta V has gotten so small that if I make this rotation any longer, then this rotation will give me less returns than I'm getting from all of the rotations combined. And so you can think of this line here. This is like the average rotation performance. So that's, this is like the average rotation performance. And you can think of this as the instantaneous performance. And so I want to make sure that at this particular point here, this is where the slope, this delta V, is going to be equal to the slope of the mean annual increment. And so that is the biological rotation. That is right at that point where those two things meet. So this, if I were to draw down here, this would be the biological rotation where those two things meet. And so the biological rotation, it maximizes revenue, but it's myopic because it does not think about the time value of money. But this is the most efficient way. This is the most wood for a given price. So if that's all I'm interested in doing is delivering the most amount of supply as possible, I do the biological rotation. But if I'm really thinking about the time value of money, then, or the opportunity costs, then I need to, then this, I may not be interested in maximizing the supply of timber to the market. So the biological rotation ignores opportunity costs. Opportunity costs that come from, for example, the money in hand is better than potential money later. So this is the time value of money. In addition, it ignores the fact that this site that I'm growing trees on, I could be doing something else with. I could sell it to somebody. So it ignores the opportunity cost of the site value. So whenever I spend time growing a tree to produce wood to sell to somebody else, that person is causing me to sacrifice the money that I could have made from not being in the timber business whatsoever. So the value of my land for something other than timber production somehow needs to go into my calculations. And then the habitat value. And so whenever I cut down a tree, that tree could have been home or at least helped support certain types of wildlife. And so there is an opportunity cost of cutting down that tree because I lose the value that I would have gotten or that someone would have gotten, society would have gotten from maintaining that habitat. So somehow I need to compensate for these opportunity costs. So how to compensate? Now, I just want to point out that, and this is the key thing, the biological rotation is the most efficient myopic rotation. It produces the most wood for a given price. Any other rotation will produce less wood for the given price. So I am going to be charging people for wood, even though they're not getting as much of it. So I'm not going to do a full market diagram where I show prices changing and all that. If we instead just think that price is fixed, if I am giving people less wood for the same price, then that means that I am effectively charging them rent. So you can think of the biological rotation. So I guess I could write that here, is the biological rotation is like the zero rent case. So this is like where, you know, marginal benefit is truly equal to marginal cost. You know, this is in the myopic sense. And so people pay for, this sort of sets the benchmark for how much wood actually costs to produce. So in this case, we are paid exactly how much wood costs to produce. So all of the other rotations, so any other rotation reduces the amount supplied, this is supposed to be amount, for a given price. And so implicitly, we have charged an economic rent on top of the cost of production. So the biological rotation effectively tells us the most efficient way to produce. It really captures the cost of production, and every other rotation, by accounting for opportunity costs, is adding in economic rent. I am asking someone to pay me more than it actually costs to produce, because me producing prevents me from doing other things. There's opportunity costs that come from the time value of money, the site value, and the habitat value. And those things are going to shift me away from the biological rotation. And the farther I go away from the biological rotation, the more rent I'm charging them to compensate me for the lost opportunity. So that's the kind of perspective I want you to get. And this connects us back to the non-renewable case. So so people were asking in, you know, in the muddiest points, you know, they're saying, I'm not quite sure the difference between the Wicksell rotation and the Faustmann rotation. The Wicksell rotation was just my way to introduce you to the time value of money when it comes to timber. The Faustmann rotation includes the Wicksell rotation inside it. It's kind of the full version. So our approach to account for opportunity costs is the Faustmann rotation. And in that case, I have to think about whenever, you know, how much value is in my land. And I think, well, when I plant, there's a cost that I pay to plant. So that's minus D. This is my cost to plant. And then after I plant, I wait a rotation length. And I am going to make P minus C times V of my rotation length. So this here is the revenue from cutting, but then tied up into the land itself, the site itself, is some additional site value. So this is the value held within land itself. And if you need a bank analogy, this here is like principal and this over here is like interest. You could say generated per rotation, or generated, by rotation. That's one way to view it. Now, I need to then decide, how do I cut in order to account for all this? Well, if this is identical to saying, how long do I keep my money in a bank whose interest rate initially grows and then falls? So how long do I keep money in a bank whose interest rate grows initially and then falls? And so what I really need is a critical interest rate to trigger movement of asset. And so basically what I need to do is to set up a rule where my computer is watching my bank account. At the instant when the bank account's interest rate crosses a particular threshold, it goes less than 5% or something like that, I pull all my money out of the bank to stop that, and I put it in another bank where the interest rate is growing again. That's what the biological rotation is doing. And so when you cut, you reset the clock on your account so that you still have this principal in the account. That just, your account, you always open the account with this principal in it. This is like the opening principal you put into the account. And then your interest starts growing. So it turns out that you're also charged a little bit of a fee. And so you open the account with this amount of money, and then the bank charges you a fee just to do business at that bank. And then you allow, then you end up getting this interest here. So so this, like, if I want to, I could say this is kind of like a bank fee. And then this is sort of the real interest. All right, so so that tells me how much revenue I've got kind of stored at any particular time. And so I need to then figure out, at what point do I pull this out and then harvest this space? So at what point do I then cut, which is equivalent to being able to sort of reset this bank account and then grow this this money again? And so in order to do that, I need to calculate the effective interest of my natural bank. And what is that interest going to look like? Well, it's going to be the additional revenue from interest. So this is the year-to-year interest. And that whole thing is then divided by my total revenue that's being stored in the natural bank account. And so I've got this thing, and the real question is this here greater than, equal to, or less than the prevailing interest rate? And so if I were to sort of plot this thing here over time, where this here is time, this is rotation duration, and this here is what I'm plotting down here. So this is being plotted in, so the top is dollars, the bottom is dollars. And so this is like plot as return. So you can think of this in percent units. And then that thing will end up looking something like this. And so return starts high and then goes, gets low. And it may even start to decline as the forest starts to shrink. I'm just drawing it during this phase of it. And so the prevailing rate of interest effectively sets a critical threshold. So this here is the prevailing. So this is R. And so at this particular point, that is the Faustmann rotation. This is when the return from the natural asset comes and meets the return that you get from a bank. At that particular point, you cut the tree, you turn the cut timber into wood, and you let it grow at the bank. Because at that point, it's going to get faster growth at the bank. And then, now that you've cut it all down, your new forest is back into its high growth. And so in your new forest, then you can go ahead and cut, which then resets the growth rate back up here. And so that allows you to then, reset on this curve. And so that's the Faustmann rotation from this kind of bank analogy. And that's where this thing comes down here. This is the revenue stored in the ground. It is the amount you've dumped into planting plus the amount you're going to get eventually from cutting, plus any additional site value that's there that represents kind of principal that's locked away. Just like principal in a bank, you can't spend it. And so, but it's still there. So principal in a bank is still there. So if you would sell the land, you'd turn the principal from the land into principal in a real bank. But we're not going to sell it. We're going to leave it in the land because we're going to continue to own the land. So long as we own that land and that land has that site value, we can think of it as principal that's locked away inside the land that we can't spend. But because we could, in principle, so to speak, turn the site into dollars, and then that would get us out of the timber business, but we would at least then be able to cash out the one time. Because we could cash out that one time and get this dump of money when we cashed out that we could then put into a bank, then we need to set our expectations on growth based on the principal that is tied up in the land. And what that does is that is going to shorten our rotation lengths. And as we shorten our rotation lengths, then we are going to reduce the amount of timber produced. And so that's the key point, is that the Faustmann rotation it shows how the opportunity costs from time and site value reduce the output of a timber farm for the same price. And so effectively, you've charged an economic rent to account for lost opportunity. And so that's just the Faustmann rotation. And it's, by the way, and it's equivalent to Wicksell when S minus D is equal to 0. So there isn't really a difference between the Wicksell and the Faustmann. The Wicksell came first, and then when people thought about this site value, then they added in, and then they said, well, actually a better model of what timber farmers are going to do is going to be the Faustmann rotation. And so the Faustmann rotation considers more things, but it answers the same question as the Wicksell rotation. There's never going to be a time where you're going to use the Wicksell rotation, because if there's no site value, you just plug in the no site value into the Faustmann rotation, and it will give you the Wicksell out. So that's all that we're saying here. The Wicksell is just meant to be a way to step us up to explaining where the Faustmann rotation comes from. Now, the only other wrinkle, are there questions about that before I review the tiny wrinkle about harvest or the habitat value? Okay. All right, so, and then generally, this, you can think of the change in rotation length is opposite in direction to the quantity R times S minus D over P minus C. So any change you make to this quantity, so if you increase your site value, then this quantity will increase. Well, increasing this quantity will decrease rotation length. If you increase price, that actually decreases this quantity. So decreasing this quantity will increase rotation length. So if you increase interest, that interest rate, that will increase this quantity. An increase in this quantity will be a decrease in rotation length. And so, so this is kind of a quick quantity that if you remember this quantity, you can remember the qualitative relationships between all of these parameters and the Faustmann rotation. Okay, so the only other wrinkle is what about habitat value or non-timber benefits? Non-timber benefits, non-timber bennies. So all habitat value does is effectively change the, if we think about the revenue from our site, then I was saying that the revenue from our site is the cost of planting plus the eventual cost of cutting and selling, plus the site value. And if I think about if I were to take all of that out and put it into a bank as my benchmark, then I would then take all of that and I'd multiply it by R, which would be the prevailing interest rate. So maybe I can make these slightly different color. So this here, I'll make, this is the, so this here is my kind of my principal or my total asset value. Maybe that's what I'll say, total asset value. And so this thing out here is my benchmark interest target. So it's how much interest I need to be gained from my rotation choice. And the book likes to point out that this whole big quantity here can be viewed as a type of marginal benefit of harvesting. And so the idea is that if I harvest now, then what you can imagine I'm doing is I'm going to take my asset value. If I've done this correctly, then what harvesting now does is it takes my asset value and it converts it into dollars, which will earn me a return of R. And so, so they view this as a marginal benefit of harvesting. I like to view it as a kind of a benchmark interest instead, because you don't actually harvest the site value every time, but the marginal benefit works for the next interpretation here. So then the idea here is then I'd say, okay, well, when do I cut? Well, I cut when my marginal benefit is equal to my marginal cost. Well, the marginal cost of harvesting is going to have two components. It will have the cost of another year's growth. So delta V is if I harvest now, then the next year's growth I lose. And so that is interest that I've lost. So that's the marginal cost of harvesting. But it will also have the habitat value. And so any habitat value that I currently am getting, and so you can think about this as like, if I internalize this, this might be money that I charge people to walk through my forest. If I cut down my forest, I'm going to lose that. So that is value that I am losing. So this can be viewed as the marginal cost of harvesting. And so setting those two things equal to each other gives me the kind of optimal rotation length. And so what adding this additional harvest does is it will have the effect of increasing our rotation length. And so in our little plots that we've been drawing, this is our rotation duration, T. And then this thing, I'm going to do dollars per year. I'll put things in dollars like the book does. And in the dollars per year, I've got my marginal benefit. I'll do in this kind of dark blue color. And it is going to be kind of shaped similar to the volume curve. So it will start low. It will start low, but not at zero. Rise and then fall. And so this here is the MB, the marginal benefit as above. And then the marginal cost curve is going to look like, I'll draw, I'm going to change the color of this habitat value to maybe be, I don't know, light green. So then if I were to draw just the delta V part of this, then it starts high. It reaches a peak somewhere in the middle here, and then eventually it hits zero down here, right about there. And so that is my P minus C times delta V. But if my habitat value kicks in for old growth forest, then once my forest gets to a particular age, then the habitat value, then the marginal cost of harvesting is going to increase by that. So I can then add in some additional component, let's say starting here, going down to like there. And so this curve represents the P minus C delta V plus the habitat value where this is only for old growth habitat. And so what we can see there is that if I don't consider the habitat value, the rotation length is going to be, this is kind of the standard Faustmann rotation. But if I consider the habitat value out here, then I see that I've actually increased the rotation length. So this rotation length includes that the additional cost that I get from cutting. And because there's an additional cost of cutting, then it sort of rescues me from the threshold. In other words, because I'm getting revenue, additional revenue from old growth forest, then that means it takes longer for the decline in growth to trigger this critical interest rate where I cut the forest down and turn it into the bank. And what I want you to see here is that if the habitat value is really large, it's really great, then it's plausible that I could actually have a case like this. So this is large habitat value. Habitat value. And if you notice in this large case here, so I'll just highlight that whole curve, it never intersects this curve down here. So if your habitat value is sufficiently large and it's internalized, then the timber farmer might decide that it's more beneficial to actually just stay in just managing the forest. Basically just conserve the forest, turn it into some sort of preserve, and just charge people for access to that preserve. Or if the government steps in and says, we will pay you to not cut your forest down, then that additional payment ends up being internalized as this additional portion of the curve. And if that payment is high enough, then basically there is that they make more money in keeping the forest alive than they do by cutting the forest down and putting it into the bank. So now if the bank interest rate goes up, then that will cause this thing to shift upwards so that they might intersect again. So that's the one thing about compensating people, is that if other things happen, so if the site value changes, if the site value increased, that would be another thing that would shift this curve up. So interest rate or site value, either one of those could shift that curve up. And so you might then need to add additional compensation. The other way to view this curve is if there is this much natural value, but it is not internalized by the timber farmer will totally ignore it and will just follow the original red line instead and cut down. And the benefit lost here is deadweight loss to the rest of society. So effectively, by cutting down, the timber farmer is maximizing his benefits or her benefits, but while imposing a cost on the rest of society. And this H is now viewed as an externality that the timber farmer is imposing on the rest of society by cutting down early. So that's kind of the big picture here, is that opportunity costs shift us away from revenue maximization, meaning that opportunity costs cause us, even in renewable resources, to effectively charge economic rents. And that's kind of what all of these rotation diagrams are meant to give you a mental model for trying to understand. As certain parameters change, how might we expect rotation lengths to change? And that is us implicitly calculating the additional rent that a farmer can generate by changing their rotation lengths based on their opportunity costs. So that's the end of what I wanted to sort of say about timber rotations. I guess the only other thing that I'll mention here is that I've made that throughout all of this, we've assumed private property. And so property rights, once again, or private goods, allow us to do these analyses. If instead it's a land of many uses and anybody can go into the forest and cut, then it may be even more difficult to ensure that, so right now, timber rotations, are pushed around by things like site value, are pushed around by habitat value. Well, all of those things are kind of they're kind of in the balance sheet of a private landowner. If you're just anybody just going into the forest, you don't realize it's site value. You don't have the ability to pave that thing and put up a parking lot. And so you're not going to pay attention to the site value. You also are not going to feel the habitat value. So when you cut down that tree, you can make use of it however you would like. And there will be the main cost will be paid by the rest of society. There is no way that you are going to be able to charge people for entry to that forest because they can get into the forest as easy as you can. So property rights allow us to actually increase conservation because that allows for the incentives such that people will actually just be incentivized to maintain things because we have internalized benefits and costs and so on. Once you get rid of property rights, it's really hard to control any of these natural resources. So it's just another kind of example of that. So before we flip gears then and focus on fisheries, which are a different type of renewal. So this, and I'll mention this more with fisheries, timber forests were meant to be an example of a slow growing renewable natural resource. Fisheries are going to be our example of a fast growing renewable natural resource. And we'll see how we change the analysis for that. So any questions then about this timber forests, which are the kind of example of slow growing, harvestable renewable resources? Pretty clear? All right. Okay, so so that is so with forests, they grow slowly, and we harvest before max growth. And if we didn't do that, the forest would naturally decline and die, or it would be renewed in sort of natural cycles, but we are not interested. So in forests, we are not concerned with natural cycles of regeneration. So all regeneration is artificial. So replanting. And that's because replanting is relatively cheap. It's pretty easy to seed a forest and let it grow. But then, in contrast to that, you could say, what about fisheries? So in fisheries, we now have, in this case, we never want to fish all of the fish in a fishery and then have to restock it. So fisheries, these are ones where we count on natural regeneration, and we maintain a stock to ensure natural regeneration. So you can view this as our principal in bank. And then the question is, how much can we harvest per year to maximize revenue and ensure sustainability. So ensure that principal is large enough to generate enough interest per year for the harvest. So that's really the key, is that we would like to harvest a little bit. It's like an annuity. So this is like an annuity. So we would like to pull some fish out of the fishery every year, but and that's just like taking money out of an annuity every year. So an annuity, you put a large amount of money down, like you put $1 million into the annuity and you let the annuity sit. If that $1 million has a 10% interest rate, and I'm not going to worry about the magic of compounding, but that means that you get $100,000 every year. So every year, if you got a 10% per annum interest rate, then that means that at the end of that year, you're going to get $1,100,000. And then you can take all $100,000, but not a penny more. Because if you don't take a penny more out, then that means that every year you're going to be able to count on having $100,000. So that $100,000 every year, that is what you're trying to get with this fishery, is that you're trying to say, how many fish can I take out to guarantee that I can take out the same amount the next year and not have to worry about my fishery eventually crashing. If you take out $150,000, your bank account isn't going to immediately go into the red, but you're not going to generate even $100,000 in the next year. So if you keep taking $150,000 out of your annuity, then eventually you will deplete the annuity all the way down to zero. To the point where it's not even possible to take out 100,000 anymore. And that's what we're trying to avoid in our fishery. And so, but we also want to make sure that we draw out as much as possible to maximize our revenue given our costs. So we need to invoke some bioeconomic models here. So in this case, we need bioeconomic models that combine fishery growth and benefits and costs. So I've got a lot of ands there. So and benefits and costs. And so let's start with the fish population. And so those of you who are sustainability students probably took SOS, SOS, I think this is probably in 101, where you learned about logistic regression and things, or not logistic regression, sorry, logistic growth models. And so those who didn't, that's fine. But basically there's a simple model of fish growth is that kind of in the naive case, so naive fish growth is that every fish has R offspring per unit time. So R is a reproduction rate. As an example, you could say, if I have one fish in the fishery, by the end of the year, I'll have 3 fish in the fishery if the reproduction rate is 2. So that would mean that that one fish had 2 fish, and then I had 3 fish total at the end. And then those 3 fish will then themselves start reproducing and go so on and so forth. And so that would be kind of be the naive, unconstrained case. But the thing is, so this naive case, this is what we refer to as exponential growth. And so what we're saying is that if you have X fish at the end of one period, you will have X plus R times X fish at the end of the next period. And then this whole thing will then cycle. And this cycling here gives you this rapid growth. So you get a, so this is time, and this is the population. And it can start rather small, but then it can grow very, very large. But trees don't grow to the sky. We know that in our forest population, the trees did have their own rapid growth, but then they eventually rounded off and then even started to decline. So in the case of our fishery, there's a finite number of resources available. Eventually, those new offspring are going to be in competition with their own parents for food. And so even though a parent might have had enough food to produce 3 offspring, 2 of those offspring are going to die because they're going to starve, and only one of the offspring is going to end up surviving. And maybe the next time around, the parent is not going to have enough food to produce 3 offspring. It'll be kind of limited to 1 offspring. So eventually, this thing kind of self-limits itself. And so so along with this reproduction rate R, so that's one critical parameter. Then we also have another critical parameter that we're going to refer to as the carrying capacity. And we typically use the letter K for that. Why K? It's because there were Germans who originally came up with these models. And those Germans, the German for capacity involves a K. And so then just historically, since we use their math, we just translate it on over and carrying capacity becomes a K. And so if we think about this carrying capacity, then basically we can say that each offspring, and sorry, what is carrying capacity? This is the maximum fish that can coexist in fishery. So based on the amount of food that we produce in, we know that every fish needs so many calories in its lifetime, where you can calculate how many calories are generated, and then you can kind of do a little bit of math, and you can say that there simply is not the energetic balance to support more than K fish, or there aren't the mineral balance. There is a balancing act going on, and there will be some limiting factor that will prevent you from putting more than that many fish in there. If you dump more than that many fish in there, a bunch will die. And then after those bunch die, probably more than the carrying capacity will die, then the rest of the fish will gradually start growing, and then we'll level off at the carrying capacity. So how do we model that? Well, what we do is we say that each offspring has a probability to survive, to find enough food to survive. And so that probability is going to be K minus X divided by K, where X is our total amount of fish. So this is our fish, this is the number of fish in the fishery. And so the numerator of this probability here, the numerator of this thing is the space that is left over. So this is the, this is the space that is left over for new fish. And so this is the probability of surviving, or basically finding enough, well, I'll just say of surviving to reproduce. So that's how we're modeling that, is that if you're far away from carrying capacity, if X is equal to 0, then this probability down here is just K divided by K, which is equal to 1. As X gets closer to K, then this numerator is going to get smaller and smaller and smaller, and this probability is going to get closer to 0. So as you get closer and closer to carrying capacity, then each new offspring will have 0 probability to survive to reproduce. So what we do is we then say that the actual rate of reproduction is going to be, so the per capita rate of reproduction is going to be R times this probability, K minus X divided by K. And this can be simplified. So simplify to be written in its more common term or common form, which is R times 1 minus X divided by K. This is just equivalent. And so this here is viewed as the per capita reproduction rate. And so what that tells me, if I combine all of that together, and I know we have about 5 minutes left, so I'm not going to forget this time. We end at 1:15. That attendance question was very helpful for me. So the total number fish produced by fishery is thus F of X, which is equal to X, the current number of fish, times the per capita reproduction rate. And this is the so-called logistic growth model. Or the Schaefer logistic growth model. I guess if we want to throw in some names there, but if you just refer to the logistic growth model, then everyone will know that this is what you mean. So this is over here. This is our current number of fish, and this is how much they're reproducing. And so this is the total reproduction rate. So if we manage for any given principal that's in the bank, so you can think of X is principal, then F of X is interest. Not interest rate, but interest, the actual interest. So these are the dollars in the bank, and these are the dollars you get out for having those dollars in the bank. And so the thought is that if we could manage to fish at exactly this rate, then we would be able to keep the system at equilibrium, where there would always be this many fish in there, and all the new fish would end up getting harvested. So the old fish would stick in there and be producing new fish, and then the new fish would get harvested and things would sit at a sustainable level. That's the kind of ideal case here. And then what we're going to see, though, is that is puts you in a very precarious position if X is very small, and it is a much safer if X is critically large. And that's what we are going to talk about probably more so next time, now that we're getting kind of the end here. But so this logistic growth model, I can plot this thing. So I'll do my axes here. So this here is going to be X. This is the current population. And this here is F of X, which is number new fish from reproduction. And if there's going to be a carrying capacity K, that's our carrying capacity. And what that's going to give me, if I were to plot that whole thing, is something that looks pretty symmetric. So that's what I'm going to try to draw, something so that I've got 1, 2, 3, 4, 5. So at about 2.5, I'm going to try to hit this point here. So I am going to draw a curve that goes up, hits a max there, and then comes down and goes to 0 at the carrying capacity. So it's not quite perfect, but it's roughly perfect, roughly correct. And so this point right here, this is the population that produces maximum growth rate. And this here is what we refer to as the maximum sustainable yield. And so this is the max sustainable yield. And so this is the number of fish harvested that ensures max revenue and sustainability. And we'll talk about that more next time because I'm at 1:15. But the basic idea here is that this is your interest and this is your principal. So this population here, you must not ever let your bank account have less than that amount of fish in it. But if you allow the fish to grow unharvested, your bank account will eventually max out at this many fish over here. And so you're allowed to take out this many fish. So this is the maximum yield that you can take out. That's the maximum interest you can take out. And if you take out that amount of interest and ensure that your principal doesn't get below this point here, then it will continue to reproduce, and it can produce enough rate. So its regeneration rate, which is right here, will be high enough to support that. So this is the amount of fish I can take out to support the maximum amount of regeneration. Any more than that, and I'm going to dip into principal, and eventually my fishery will go extinct. All right, so that's where I'm going to stop today. We'll pick up there next time. So I'll give you your attendance question here, and I'll put the link in the chat. Oh. Which is right here, bit.ly. And the attendance question I'll give you is how does economic rent change as you add opportunity costs to rotation calculation? So does economic rent go up or down as you incorporate more opportunity costs into your rotation calculation? That's your attendance question. And that's all I've got for you today. I'm happy to stick around for questions. Sorry to keep you a little bit over, and we'll pick up with fisheries next time.
Thank you so much. Have a great day.
You too. All right, looks like everybody is heading out.
I actually had a quick question about the homework.
Sure.
So I was doing problem 6, and I got kind of stuck on the scarcity rent question. Just because every time I looked at my notes, it said it required R, but I couldn't find R in the problem. So yeah, I got a little stuck there.
Sure, let me open up the homework on my end so that I can make sure that I'm calibrated. And so question 6.
I believe it was 6 F or yeah.
6F, okay. What is the scarcity rent achieved for, okay, yeah. So in this case, 25 units, extraction, marginal benefit. All right, so yeah, so the okay, yeah. So So in this case, we're taking a myopic perspective. And so, so this is, and in some ways, it's, I don't want to call it a trick question. They're never trick questions. But the idea here is that for 6, and you're considering the myopic case, is because you're considering the myopic case, just like we talked about today, you're kind of ignoring that interest rate exists. And so if you take the myopic case, you know how much you're going to produce this year and next year. The scarcity rent is just defined as the amount of extra revenue that you generate above the cost per barrel. And so you should be able to calculate that even without an interest rate. Now, in part 7, or in question 7, I give you an interest rate and I say at the optimal, what would the scarcity rent be? That's the optimal scarcity rent. In part 6, you still calculate a scarcity rent, but it's just not the optimal scarcity rent.
Okay. So sorry, I'm trying to see exactly what I did here. Will I just be like subtracting 2 numbers from each other? Because that's kind of I can't. Sorry.
Yeah, right.
I'm
Yeah,
trying to read exactly what I did, but I'm kind of confused what I was doing.
I mean, yeah, the scarcity rent will just be subtracting 2 numbers from each other. So, so basically, what you should do in part 1, all of question 6, you've already done some of this, but in part 6F, all you need to do is calculate how much you're going to supply next year, which is just however much you didn't supply this year of the total. And then with that, you should be able to calculate the price that people will pay you for that. Because you will supply a low amount next year, that price will be high. So then if you then subtract the cost that the cost of extracting those barrels, then there will be a difference between the price you charge and the cost you paid to extract them. And that difference is the scarcity rent.
Okay. So here I have, so it would be like so like price 2 minus just like, wouldn't be the marginal cost, would it? It would be price 2 minus marginal cost?
That's right. Price 2 is the marginal benefit that you get in year 2, and the marginal cost is the marginal cost. So marginal just means per barrel or per unit benefit. So the per barrel benefit is marginal benefit in year 2. The per barrel cost is the marginal cost.
Okay, but I wouldn't like, because it is per barrel, like for example, like this is like the marginal cost is 100. So I wouldn't like multiply it by like the quantity or anything, right? I would just do like the price 2 minus 100. That's kind of what I was confused about. Sure.
Right. The scarcity rent is also a marginal quantity. It's kind of like the rent on your apartment is per month. So it's the additional cost that the consumers are going to pay per barrel above the cost you paid to get the barrel to them.
Okay. I think that makes sense. Okay, thank you.
Sure. Any other questions from those who've hung out?
Professor, I got a question. It was regarding the attendance exercise, just making sure, because that's the part I was confused. So like overall, the economic rent decreases when you add opportunity cost to the calculation, right? Because just another.
Did you say increase or decrease?
Yeah, the economic rent increases as you add opportunity cost of rotation.
That's right. That's right.
Okay, just making sure. Like I just need another quick rundown, like how it affects it, how to increase the economic rent again when you add opportunity cost.
Right. So the economic rent is what you're charging consumers so I directly charge consumers for whatever I supply them. The economic rent is what I charge them in excess of that for the other things that I could be doing with the thing that I needed in order to supply them to that. So in the case of the timber farm, I charge them directly for the cost of the wood, but then I also charge them a little bit extra because I could be doing other things other than timber farming. And so I need them to compensate me for just being a timber farmer on top of the actual cost of the timber. So the more things that I could be doing with my time, with my space, etc., the more I'm going to charge the consumer, because because in other words, if I only make money on the timber, then
You could
what
be doing
keeps me
something
in
else.
timber farming? Exactly, right. And
Okay,
so
got it.
that's why they've got to pay me to stay in the job.
Okay, gotcha. Thank you so much, Professor.
Sure. Any other questions?
I had a quick question about the bonus for the homework that was like due tonight.
Yep.
Okay, so when it was like talking about the intertemporal marginal net benefit diagram, is it just like asking for the one for like the marginal net benefit, like the one line, rather than having like both of the marginal net benefits? Does that make sense?
I'm looking for the whole cross, and so
Okay.
I realize I'm still sharing my screen here, but yeah, the full. You've already kind of, I think in an earlier problem, I asked you to draw one of these like without labeling the axes. I think I forget which question that was. Question 5. So it's kind of everything that you would draw in question 5, but rather than just drawing it in the abstract, I want you to label everything. So label all of the numerical values on both axes, or actually on all 3 axes, on the horizontal axes and the 2 vertical axes, and all the intersection points.
Okay, awesome. Thank you so much.
Sure. Any other questions? Excellent questions. All right. I see no other microphones going off mute. So I will assume that's everything, and I'll see everyone on Thursday, and have a good week.
Thank you, you too.